start recording. Move this out of the way. So I'm just rearranging some things on my screen. Okay. So a tree is actually a recursive data structure, and you've seen trees before. If you've seen a family tree, let's say you have Peter and Mary who begat, say, Joe, Lisa, and Nancy. So this would be a family tree. Maybe Joe married Kate. Maybe Lisa stayed single and Nancy married Fred. So Joe and Kate perhaps had Sarah and Frank. Maybe Fred and Nancy just had one child, Caleb. So that's a tree. You've seen family trees before, I presume. You've probably also seen organization charts. So for example, you might have a president, and then you might have some big vice presidents like of sales, vice president of finance, maybe a vice president of, say, engineering. Then under them, they might have some things like the district manager for District 1, manager for District 2, maybe a manager for District 3. For finance, maybe there's someone who manages accounting. Maybe there's a manager for HR. For engineering, maybe there's a manager for the, let's see, chassis of our product. Maybe there's another manager for the engine, and so on and so forth. So again, this is a tree. And the book went over the definitions, so I'm not going to go over the definitions. What I do want to point out is that a tree is a recursive data structure. So in fact, the base case for a tree is the leaf. So a tree, the base case is a single node, which is a leaf. Okay, that's the base case. Then the recursive case is an interior node with one or more children. And the way we show that is with a triangle, because if you look at how the trees look, they kind of look like a big triangle. So we are showing a tree as a triangle. So this is the recursive case. You have a root. So this is the root. And it has one or more subtrees. So one or more subtrees. So it's a recursive structure. Now, computer science, we deal with trees all the time. The trees we're going to care about in this course are binary search trees. So, binary search trees are search trees in which everything in the left subtree is less than the root, and everything in the right subtree is greater than the root. So here, Binky is less than Fred, Luther is greater than Fred. Over here, Fred's greater than Binky. Daisy is greater than Binky, but less than Fred. Luther is greater than Binky and greater than Fred. Luigi, greater than Binky, greater than Fred, greater than Luther, less than Luigi. So a binary search tree has at most 2 children, hence binary. And as I said, a guarantee that all nodes in the left subtree are less than the root, and all values in the root subtree are greater than. Okay, so doing an annotation. With the binary tree, we have a key K. Everything in the left tree is, I'm going to make this bigger, less than K. Everything in the right subtree, greater than K. For the time being, we're not going to worry about duplicates. If we worry about duplicates, then we typically would put either the duplicates in the right subtree or the left subtree. It would be arbitrary. Okay, so Dr. Planck shows some examples of non-binary search trees. So here, Daisy is greater than Binky, not less than Binky. So is Luigi and Luther. So it's not a binary search tree. Here, we have too many children, so it's not a binary search tree. Okay, today we're going to go over insert, delete, and if we have time, traversals. On a week from today, Tuesday, we're going to go over deletion and some of the operations you're going to need to do for Lab 10. So you can, it turns out, do find and insert quite easily. So find, we've actually kind of already done it. Actually, before we do that, I want you all to take a moment to create your own binary search trees to make sure you know how to do them. So what I'm going to do is give y'all some numbers. I'm going to give you those numbers. Try to quickly create a binary search tree. Assume they're given to you in that order. So 8's given to you first, then 3, then 10, then 6, then 1, then 20, then 2. So take about 2 minutes and see if you can't draw your own binary search tree. I'm going to give you about 2 minutes to do that. And if you have a question, just let me know. See, you can either interject or you can raise your hand. Chris, do you have a question or not? Hey, Georgia, go ahead.
Yeah, it's about the test. I was wondering, can you, do you mind updating Piazza with the information you told us? Because I still think it says that both are open node on Piazza.
I will do so. Thanks, Georgia. Yeah, I'll put down the instructions for the Respondus browser too.
Okay, thank you.
Welcome. Okay, so I'm going to go ahead and show you what the binary tree should look like. So 8's our first thing, and it becomes the root. So always the first value we get becomes the root. Then 3 is less than 8, so it's put here. 10 is greater than 8, so it goes as the right subchild of 8. Now 6 is less than 8, so we go to 3, and it's greater than 3, so we make it the right child of 3. Now we are looking at 1. 1 is less than 8. 1 is less than 3, so we make it the left child of 3. Now we insert 20. So 20 is greater than 8. 20 is greater than 10, so we make it a right child of 10. And finally, 2 is less than 8. It's less than 3, and it's greater than 1, so we make it a right child of 1. So that's the binary tree we get. Any questions about that? Okay. Now, if the keys are pretty much in random order, you'll tend to get a pretty balanced tree like you see here. But you can have bad orders. If I have 1, 2, 3, 4, 5, my tree is going to be a big, long, linear list, which is going to be the drawback for binary search trees. In this case, we say that the height of the tree is order n, which is bad. But if it's balanced, which is generally the case, the height is order log n, which is a lot better because, as you saw, when we were doing our inserts, we only had to look at one key at each level in the tree. So if there's log n levels, we only look at log n keys. That's a lot faster than n. Don't worry about getting unbalanced trees right now. We will worry about that in a week or so. So all we're caring about now is the algorithms for inserting, deleting, finding keys in a tree, and then doing traversals on a binary search tree. Before I forget, I also want to make a quick note. Dr. Planck has a different definition of height than the book. So in the book, they define the height of a node. So book's definition as 0. Dr. Planck definition of height of a single node is 1. So in the labs, you'll use Dr. Planck's definition. And that makes a difference because if you, so let's look at this tree right here. The book would say this tree has a height of 1 because height of that node is 0. The height of that node becomes 1, which is the maximum of the heights of its left and right children. The height of this node is 0, so the height of this node is 2. So the book would say the height of this tree is 2. Dr. Planck would say that the height of this tree is 3. And the reason he would say it's 3 is because he would say the height is 1, the height there is 2, the height here is 1, and so his final height would be 3. So I just wanted to be clear that Dr. Planck has a slightly different definition of height because his base case is different. So questions about that? It's something you will probably want to put in the notes because it is a divergence from the book. Okay. Now, next thing. Dr. Planck's implementation of a binary search tree is a bit different than the book's implementation of a binary search tree. We're going to be using Dr. Planck's implementation of a binary search tree, and he's going to use a sentinel node. So in his implementation, if you have a tree, I'll just have a simple tree like this. Actually, I'll give it one more child. He has a bunch of sentinel nodes. So actually, I'll denote the sentinel node with a X. So conceptually, this is what it looks like. So every leaf, anything that doesn't have a child actually points to a sentinel node, which I'm denoting with X's. And at the top of his tree, he also has a sentinel node whose right child points to the root. This is not how the tree is actually implemented. This is just conceptual. This is how the tree is actually implemented. There's only one sentinel node. And every node points back to that sentinel node. Sorry, every empty child points back to that sentinel node. So in fact, he has only one sentinel node for the entire tree. Okay, again, the sentinel node is going to get rid of special cases. So why do we use a sentinel node? Gets rid of special cases. Kind of. You'll see that it still has to do something. But in the book had to do, I think, 3 different lines of code for the root case where you're inserting the first value versus all other cases. So let's take a look at Dr. Planck's data structure for a binary search tree. And you can see he is using a BST node with a left and right child pointers, so left and right child pointers. He also is going to point to the parent. Then he is keeping a key as the string value. And we haven't really gone over voids yet. He doesn't want to make you deal with templates just yet. So with templates, you're able to say something like, say, you can say B tree or BS tree, say int string. But he doesn't want you to have to deal with templates. So what he's going to do is force the key to just be a string, but he still would like the value field to be as arbitrary as possible. And so what he does is he makes the value field be a void star. A void star can point to anything. So essentially, just like a int, in some sense, is a subtype of a float, so every pointer is in some sense a subtype of a void star. So you can store anything. A void star can point to anything it wants. So that means you can put anything into the value field. Now to unpack something, so when we store something, we actually can just say val. Let's say we had a person and we had a void star val. We can always say val equals p. Just like if we have a float, f, actually we use doubles. I don't want to get in the bad habit of using floats. And an int I, you can always say f equals I because that doesn't lose precision. But if you want to go the opposite way, you're going to have to do what we call a downcast. You have to say person star val. And this is called a downcast. Okay, because in some sense it is casting from a void down to a person. Now, you oftentimes, for clarity, would still put a void star here, but it's not necessary. The compiler won't complain. Okay, but let's just take a look at that. So I'm going to bring up a window just to show you. Oops. I get rid of all my erasing. So I'm going to create a program called pointer, and we'll call it void pointer. I don't even need a pound sign include. I'm just going to create a int main. I'm going to create a int star int pointer and a void star void pointer. And I am going to say void pointer equals I pointer and try to compile it. And there should be no trouble with this. So okay, so there it is. I'm going to bring in a second window. And it compiled okay. And that's because going from an I integer pointer to a void pointer is just fine. Now we're going to reverse it and try to assign the void pointer to an I pointer. And we're going to compile that and get an error message. Assigning to an int star from an incompatible type. So we're going from something that is more general to something that's more specific. So here the downcast is required. Once we do the downcast, C++ is happy. Okay, so you use a void star when you want to store an arbitrary value in a field. So use a void star although it has to be a pointer. So it does have to be a pointer, but you can store anything in there. So questions about that? Okay, looks like I do not have questions, so I'm going to keep going on. So Dr. Planck has some constructors. It has a copy constructor. Right here's the copy constructor. The two functions we care about right now are the insert and find functions. So find is going to take a key. It's going to return the value associated with that key. It's declared it's const because it doesn't modify the tree. Insert will modify the tree. It tries to insert a key with the given value. Okay, and temporarily, we're not going to worry about these other functions. You can see we use a sentinel, which is going to point to the root node. We also are keeping track of the size. We are not going to worry right now about these recursive functions because they are for the next lecture. Before we look at the code, I do want to point out namespace cs140. Namespaces are a new concept. They look a bit like a class, except that instead of class, they have the keyword namespace, and then a curly brace and the end down here with a curly brace and a semicolon. And what they do is they divide up our namespace. So conceptually, everything that we have in cs140 is now in its own namespace. So in fact, in the cs140 namespace, we have BST node and we have BS tree. So if we simply tried in main to declare a BST node, it wouldn't work. In fact, let me again illustrate by going to a file and actually showing you the particulars. So we will do namespace.cpp. So I'm going to do a class. I'm going to say namespace cs140, and then I'm going to put a class person. Just for simplicity right now, int x, int y. Let's make it a point, because that would look more like a point. So there's our namespace cs140. Now I'm going to try to declare a point p, and you're going to see that when I compile it, whoops, I'm going to get an error message. So error, no such file or directory namespace. Whoops. I just didn't compile that correctly. There we go. So unknown, so the problem is on line 10. This is line 10. Unknown type name point. Did you mean CS140 : point? So with namespaces, they kind of put boundaries around our namespace or around our variable. So they can't be seen outside that namespace unless we do one of three things. You're used to doing this. You're used to saying using namespace cs140. When you do that, all the types that you declared in cs140 and all the variables become visible in main or are in this namespace. So if we now compile this and run it, it works properly. Okay, there's no whoops, sorry. It works properly, it compiles. Okay, sometimes though, you would have something like this. You might have another namespace. And it has the same thing in it. You say, why do that? Well, that's the whole point of namespaces, so you can repeat things. So they're separated from each other. So now if I say using namespace cs140 and using namespace cs360, the compiler is not going to be happy. And the reason is there's a conflict between cs140 point and cs360 point. So we could now disambiguate by saying cs140 : point. And if we compile it, it's happy again. Okay, so putting the namespace : indicates what namespace it's part of. Finally, I could have simply said using namespace cs140 : point. And then again down here, I'm going to get rid of this. Actually, did not like that. So let me quickly see what the third way is, because that's not the right syntax. Using. What did I say? Using. Just cs140. So if I'm going to say using, I could then no namespace, and the compilation worked. So in that case, there was no namespace. So three different ways of including something from a namespace: say using namespace, or just the name of the class we want to use, or we always preface the class with the namespace. So questions about namespaces? Okay. I don't think Dr. Plank makes extensive use of namespaces in this course. You'll learn more about them possibly in 302, definitely in 365. With that, what I want to do is now move on and look at the find and insert for a binary search tree. Okay, so find is pretty simple. We declare a variable n, and we immediately make n point to the node that the sentinel points to. So for example, if what we had was a sentinel node, and let's say it pointed to 8, then 8 pointed to 6, and 10, and 3, and 7. So let's say we're trying to find the key, the string 7. So n initially is going to point to 8, because that is what the sentinel's right points to. So sentinel points to this node. Now we go into an infinite loop. We ask if the n is equal to the sentinel. If it is, we return null because we didn't find anything. We didn't find the key. Otherwise, we check to see if the key is equal to the key at that spot. So the key in this case is 7. And that's not equal to 8. So we come down to here and we set n equal to the result of comparing the key with n of key. Well, 7 is less than 8, so we go to true. And we set n to be n of left. So now n no longer points here, but instead points to 6. Okay, we again check to see whether n is null. It's not. So we check to see if n is null. It's not. Now we check to see if it's equal to the key. It's not. We ask, is the key, which is 7, less than 6? False. So we take the right branch, and n now points to 7. Okay, again, we do our comparison with the sentinel. It's false. Now we ask, is key equal to key? And the answer is yes, because 7 equals 7. So we'd return whatever value is now at 7. Okay, and let's say instead we had been looking for, instead of 7, let's say we were looking for, come on, say we were looking for 9, then what would happen is n would start at 8, because n is greater than 8, n would now look at 10. Now remember, 10's left and right children point back to the sentinel. So when we get down to 10, we find out that 9, our key over here, is less than 10. So we go to n left. N left is the sentinel node. So n becomes equal to the sentinel node at this point. And when we come back up to here, we now return null. So that's what happens if we try to find a key that's not in the tree. So questions about find. Okay, no questions. So we're going to move on then to insert. So insert starts out just like find, because it has to find the place in the tree to do the insertion. So for example, if we are trying to insert, say, let's go up here. So let's say we wanted, let's say we wanted to insert Caleb. We would first need to find where Caleb should be inserted. So it'd be like a find. We'd go to Fred, then to Daisy, and then find that Caleb should be inserted with Daisy. So coming down to the insert, we're first going to go as though we are finding the plate. Well, we do. We find the node where we're going to do the insert. And we also keep track of the parent. So what we're going to do in this case let's say that what we're doing is, oops, don't want that. Let's say we want to insert 7. So we start out with the parent pointing to the sentinel node and n pointing to 8 because n is equal to the sentinel right. Then we're simply sliding, this code simply keeps sliding the parent to point to n and n to point to the next node. So 7 is less than 8, so we make n point to 6. Now we find that 7 is greater than 6, so we're going to make the parent now point to n, and n is going to be made to point to 6's right. Well, 6's right is the sentinel node. Okay, 6's right is the sentinel node. So n now points also to the sentinel node, and we're done. It says while n is not equal to the sentinel. Okay, notice if he actually finds the key at any point, he returns false. So this line, if he finds the key in the tree, he returns false because he doesn't want any duplicates. Otherwise, when he's done, he's going to eventually reach a sentinel node because the key is not in the tree, and the parent is going to point to the location where we should insert the node. So now we create the node, assign the key and the value to the node. N's parent is the parent, and n's left and right are set to the sentinel node because it's a leaf. So this is all right now, essentially n points to a new node. So right now, we've made n actually no longer point to the sentinel, but it instead points to a new one with a key of 7, an appropriate val field, and we're making its left and its right both point to the sentinel node. Okay, now we just need to link n into the tree. So our last step is to, first of all, check to see if the parent is the sentinel, because if the parent is the sentinel, it means that this is the first node into the tree, and we make it the root. So you can check that. I don't have time, but you can check that on your own, that if there is no node in the tree, then that loop, this loop up here, is going to immediately exit because n will be equal to the sentinel node, and we'll be done. Just a moment, Blake. I see your hand. So if otherwise, we have to figure out whether the new node should be inserted as a left child or a right child. In this case, the key 7 is not less. We are asking whether 7 is less than 6, because 7 is the new key. The answer is false. So we're going to make the parent, which is 6, point to our new child. And then we finally increment size, always an important thing to remember, and return true. Okay, so I know I went through it a little bit quickly, but I think the code is fairly straightforward. Blake, you had a question.
Yeah, I was wondering, so this isn't directly related to what we were just talking about, but it's for the after lecture problem.
Yeah.
And I was just wondering where we find like the input files and the solution binary and stuff.
Okay, perfect. Thank you for raising it. So last thing, there is an after-class activity today, which is not due until after the exam, although honestly, it is good practice for the exam. And in fact, it was a problem I assigned before
Yeah.
the break, but the code assessor went down, and so I just redid it. And in fact, you can now simply click through. And it gives you a problem description. And if you go to the bottom, what to do, I see, sorry. I will add the file. I see the directory. The directory, I'm just going to write it here. It is, if you log in, it's home, but I will put down the directory so you can see it. It is
Okay.
home, come on. I will modify the file so it has it. It's home, B Vander Z, cs140, capital L labs, so in your labs directory, and it's called best name and is capitalized. So that's where all the files are. And you'll upload it to the after lecture link right down here. So I'll add that directory. You've got a week to do it. Like I say, though, it's really good practice for the midterm. Other questions? Okay, in that case, I'll let you go. I will see you Thursday. TAs will see you tomorrow in lab.
Oh, I have a
Go
question real
ahead.
quickly.
Sorry, go ahead. Actually, I'm going to let
Sorry.
everyone else go because we're 5 minutes over. And let's see. I don't see who's talking, but.
It's Andrew. Thanks.
Oh, wait, who is it? Go ahead.
All right. So this is about the exam on Thursday.
Yep.
So my desktop doesn't have a webcam, and my Chromebook does, but I don't think I'll be able to download that browser on there unless it's like, because with Chromebooks, really the only thing you can download is something that's like in the Google App Store.
Okay.
So
Send me some email, okay? So the first thing, try to see if you can't download the Respondus software, okay? Because you might be able to use it without a webcam.
okay.
So just see if you can download it to your Chromebook. If you can't download it to your Chromebook, try to download it to your laptop and at least see if you can use the browser that way, okay? Without the webcam.
Okay.
And send me
All right.
some email about it before Thursday.
Gotcha.
Okay, thanks.
Yeah, somebody in the chat just said Respondus isn't compatible with Chromebooks.
Okay, someone just said Respondus isn't compatible with Chromebooks, so don't even worry about that.
Okay, I'll just try to
Just
get it on
download it, Andrew, to your
my desktop.
laptop.
Yeah. All right. Thank you.
Welcome.
Bye. Thank you.
Welcome.
So is best name is best name the same program as like the best last name, or is there something different?
Yeah, it's the same as best last name.
Okay. And you're saying that would be good review for the test, so it might be a good idea to like look over it and like, you
Yep.
know, like go over it.
This is, yeah, pretty much a freebie. There's a way to find the answer.
All right.
I'll tell you that. If you're sufficiently motivated. So if you can't get it on your own, there's a way to figure out the solution.
All right.
Yeah, it's good practice.
Yeah, I think I got that one right. So.
Okay.
All right, thanks. I appreciate it.
Welcome, Nathaniel. Other questions? Yes, Catherine. Or Peter. Whoops. Peter or Catherine?
Yeah.
How you doing? Peter.
So, for the best name, will it still be on Code Assessor?
No. So I changed it so it doesn't use Code Assessor. You're just going to go to that directory I just showed you. I'm going to add it to the what to do. So you just create your own directory called best name, And then you'll copy those files into it. You will compile it in that, write your own bestname.cpp file, compile it in that directory, and then use the grade script to check it.
Okay, perfect.
Out of curiosity, did you do something with palindrome in the lab last Wednesday or not?
Yeah, we did.
Okay, it's going to be similar to what you did last Wednesday.
Okay, perfect.
Okay?
And another question for the exam tomorrow. So this Respondus app, is that the only application you have to download to be able to take these exams? Or is there
Yes,
something else?
that should be all you have to download.
Okay.
And Canvas should tell you how to do it. UTK, if you go to the course and scroll down on the left, you should see, I believe, Respondus software. My issue is I can't get a student view, I don't think, just like I'm going to online. There might be a way for me to get a student view, but I'm never sure how to do it. So I unfortunately but see on the left-hand side of mine, I have a lockdown browser, and I think you have something similar.
Okay.
So it should give you instructions about how to get it downloaded. Like I said, I'm going to put together a short quiz worth nothing, just something to give you some experience with it.
Okay, perfect. Thank you.
Derek, looks like you have a question.
Yes. For tomorrow's coding portion, what are we allowed to access?
Anything you want. You can't access outside help, meaning you can't talk to anyone else, but you can look
But
at,
are we allowed to
you can
look
look
up
at the
syntax?
guidebook. If you want to Google for the syntax for a function, you can. If you want to try to compile it, which I don't really recommend, you can.
Okay.
Or you can try to compile it. You can't really, I'm not giving you enough scaffolding to execute it.
Okay. And also for the Respondus part, it's just for Thursday. We
Yes.
don't need that ready by tomorrow.
No, not by tomorrow, just by Thursday.
Okay. All right, thank
Tomorrow's
you.
just a regular Canvas test,
Okay.
like you did the first time.
Oh, and also, if I don't have a webcam either, is that okay? Or would you?
It's
Because I could use
probably
my.
going to be okay. But
Okay.
what were you going to say you could use?
I have a laptop that I could use, but if it's not required, then I'd rather just use my desktop. But
I would rather you have a webcam if possible.
okay.
Why don't you want to use your laptop, just out of curiosity?
Well, I'm just on my desktop, and it's a larger monitor.
Yeah, I got you.
That's really it. So it's not an issue. I could just.
Yeah, I'd really rather have you use a laptop, so I can get you with the webcam.
Okay. All right. Thank you.
Okay. You're welcome, Derek. Other questions? Keter, do you have a question? No?
Yeah, I do. So basically on top of that question, so for like you said, tomorrow we'd be able to, like look at other resources, for the coding portion if we wanted to look up syntax or something. So would we be able to do the same thing on the paper version? Is that the reason we're using Respondus on Thursday?
No, I don't want you to be able to do that for the paper version.
Okay.
I basically want to force you to just use that laptop with no outside notes. Hence the webcam as well.
Okay, so for the paper version, we can't have any notes or any
Correct.
book
You
or anything.
cannot have any notes.
Okay, perfect. Okay, sounds good.
Okay. Catherine, did you have a question?
No questions here.
Okay, no questions there. Nathaniel, any questions?
Yeah, I just had a follow-up question. So for the best name, if we did it on Code Assessor, do we have to
You're good. Don't worry. If you already did on Code Assessor, you're good.
Okay.
Don't
Because you
worry
were saying
about it. You'll get credit. Yeah.
All right, sounds good then.
Okay.
Appreciate
You're welcome. And Nathaniel, I got another class in 3 minutes, so I have to take off. If you have more questions, I'm going to be in office hours at 3:30. Same place, same channel.
All right, thank you. Appreciate it.
Okay, you're welcome. Bye-bye.